So hello there and welcome to another tutorial. My name is Henry Bakshi and this time we're going to be going over something that I call the Amazing Maze. Now what could the Amazing Maze be? Out of all the amazing inventions that I make on my channel, what could this be? Well, this is using the A-star pathfinding algorithm, which is different than the Dijkstra and best first search algorithm in many ways. This is a pathfinding algorithm that will allow us to find a way from point A to point B, even through a maze, pretty easily. So I've made a Swift version of this, and today I'm going to be explaining it to you. First I'm going to explain the algorithm itself, and then I'm going to be explaining my app that I created on it. Right now you can get auxiliary code for this app down in the description. However, in a while I will be posting up the actual API for pathfinding that I will release, so just keep your eyes in the description for that. You will get it soon, and yeah. So let's get started. So this is called the A-star pathfinding algorithm. It's different than the best first search algorithm, which is very greedy, with the fact that it also keeps a track of how far it is from its root node, meaning its point A. So it will keep track of both how far it is from its ending point and also how far it is from point A, which is the starting point. And it's also different from the Dijkstra algorithm because the Dijkstra algorithm will also search a lot of unneeded nodes, which it really shouldn't be searching at all. I mean, if it knows it's right there, it shouldn't go over here and start searching. It should just go over there, which is what the A-star pathfinding algorithm will solve. It will find usually the shortest path to the end. And this will work great in games where an AI entity would need to actually find its way to a player from so many nodes away, so it can just find its way through, ignore obstacles, go around obstacles, stuff like that. Let's get started. So before we even start learning about the A-star algorithm, we need 3 different costs. What is a cost, you may ask? A cost is the amount of energy used by a node. So for example, there are 3 different types of costs that you have in this sort of an algorithm. There's the G cost, there's the H cost, and there's the F cost. The F cost is always the main cost here. It's like the father of all costs here. So this cost is always equal to G plus H, which I will explain in just a minute. Now our G cost, and you should know a cost by now because I've explained it, it's how much energy is used up from one specific node to another node. Our G cost will be the energy used from one node to its starting point, meaning, let's just say we take this path. This node will have a G value of 10, then 20, then 30, then 40, then 50, then 60, due to the fact that this is point A, its G value is 0 because it is itself point A. Then we add 10 here, we get 10. Then 10, we get 20. Then 10, we get 30, etc., etc. So our algorithm here to find the G value is always going to be the last G value plus another 10. So that's how we find our next G value. But how do we find our H value? But first of all, what is our H value? Our H value is how much cost we have for moving from this node to our ending node. So the way you calculate this, and before I tell you, let's just draw the coordinates on this grid so we can actually understand it. So first I'm going to draw the Y values, 0, 1, 2, 3, 0, 1, 2, 3. Perfect. So now we can see that this is 0, 3, this is 3, 3, this is 3, 0, and this is 0, 0. So that's how we can understand our grid now, so we can find the coordinates of any such grid like this would be 1, 2, etc., etc. So now, let's see how we calculate the H value. Since this is a longer expression, I'm just going to write it down here. So this is where we're going to do the H value. Okay, so now let's get started by doing, this is the actual algorithm. we find the absolute value of the nodes x minus the ending x plus the absolute value of the node y minus the node, the end and y. Okay, so we add these, and then one more step, we multiply it by 40. This will get us our h cost. That's a pretty long expression. Thank God we have computers to do it. Anyway, so then once we find our g and h costs, we always have to find our f cost, which is going to be g plus h. So Swift's, forgot what it's called, but they have a feature where you can just set, you can give a variable a getter and a setter. So instead of having to set the f value each time and then retrieving it, you can just retrieve the f value and it'll always return g plus h. That's a really good feature. I'll have that written down in the Mac part of the video. Anyway, coming back to our A-star explanation. Now you know what each of these costs are. And so now, as you can see over here, I've prepared a little demonstration of how this entire A-star pathfinding will work. Remember, this is not my app. This is just a presentation that I created, which will explain exactly how the app will traverse through point A, go along here, come up to point B. So it's just a little explanation of how that happens. So now what I'm going to do is I'm just going to give you one more quick demo over here. Then we're going to get over here, see how this actually works, and then we'll go to the code. So as you can see over here, let's just give a quick example. Over here, let's just find the G, H, and F costs for this specific node. That's it, and then we'll go to our explanation. So in order to find the G cost, we take the last G cost. In this case, it was 0 because it's itself. Then we add 10 to it, and you might be thinking, why do we add 10 to our G cost? Is there a special reason? Well, there is. First of all, this app cannot do diagonals. The reason I didn't program them in is because let's say there's an obstacle here, let's say there's an obstacle here. Our diagonal searching won't look for an obstacle over here and over here. It's just going to look if there's an obstacle here, and it'll just happily jump over these obstacles and continue and continue and continue, which we do not want, obviously, so we don't do diagonals. Coming back to the point, let's find the G, H, and F values for this specific node. So as you can see, we've already calculated the G cost, which will be 10 due to it being the first node that we're traveling to. Then what we do is we calculate the H value. So our node X, okay, let's just actually fill in the blanks over here. We have absolute value, node X minus end X plus, I'm just going to remember to put the absolute value here since I don't want to write that, or actually why not. Absolute value for this minus this plus the absolute value for something minus something times 40. Okay, let's fill in the blanks and actually answer this equation. So first, let's take this by parts, okay? So we have the absolute value. What's the node's X value? It's 0. Or, yeah, the node's X value is 0. So we're going to fill that in. What's our ending X value? 3. Okay, so I'm going to enter that in. Then, what's our Y value for this node? It is 2. So I'm going to enter in 2. What's our Y value for this? 0. So I'm going to enter in 0. So what would this be? This would be 3. And you might be asking yourself, why would it be 3? 0 minus 3 would obviously be negative 3. Well, you obviously ignored the fact that this is an absolute value, meaning that we have to take away that little negative that's over there. Apart from that, we have the plus symbol, and I'm just going to put this in a bracket, plus, and now we find the absolute value of 2 minus 0. That would obviously just be a positive 2. Then we can close our bracket, and then obviously times 40. So let's just take this by parts again. I'm just going to break this down into a little expression tree. So then this would be 5 times 40. So our final equation will be 5 times 40. So this will be 200. Okay, so now that we found out our h value, we can just write it down here. And so our f value will obviously be 200 plus 10, which will be 210. Perfect. So this will be our final node. This is how the computer will interpret this node, and we will be able to get a proper functioning A-star working algorithm just by choosing the lowest f value on the entire map each time when we take another move. That's pretty simple now. So yeah, I'll meet you at the presentation part of the video. So, just before we get to the presentation part, I'm going to explain the little template. And so now that you know the G, H, and F values, you should be able to get this. So for each node that I have on my little presentation over there, I will have it formatted this way. Up in this corner will be the G value, the H value, and the F value. Again, this is the cost from our starting node, or root node. This is our heuristic value calculated using the Manhattan method, which I will explain later. Value to our destination square. Then our f value, which is our g plus h value. So let's get started, shall we? So let's just show the presentation really quickly. And so now let's get started. Since I've already showed you a little example of it calculating this node's g, h, and f values, I'm just going to tell you that this was actually right. What we calculated was correct, and so there's a 10, 200, and 210, as you can tell. Okay, coming back to our presentation. Then it will calculate the G, H, and F values for its next neighbor. So it'll look at all its neighbors and say, okay, I can either go to this, either go to this. Calculate the math for each one of these, then choose one. Now, you must be asking yourself, why are these both the same? They shouldn't be. Well, actually they should. Because let's count. 1, 2, 3, 4. Okay, 1, 2, 3, 4. That means it's the same amount of squares away than the other square. So these will both be the same. However, I programmed it to choose right more than up and up more than left. So now it goes over there. And now I'm going to speed things up by calculating 2 at a time so that we don't take all day. So as you can see, it calculated the G, H, and F values for its neighbors as well. So its neighbors were this and this. So 20, 160, 180. They're getting smaller each time. Again, 20, 160, 180, because they're the same amount of squares away. 1, 2, 3, 1, 2, 3. So those will be the same. Then it decides to go over here again, because it detected that, okay, I could either go up here, where it's 31, 20, 150, or I could go where it's 31, 20, 150. However, this is right, this is up, and again, it chooses right over up each time. After that, it sees that I have no neighbor but this one, so it'll calculate the values for this one. It'll look for the smallest f value on the entire map, and not just over here, it'll actually look over here too. And it'll say, oh, if this one's f value is coincidentally smaller, then we just want to backtrace and go through here instead. But it found out that the f value is smallest over here, so it continued in this direction. And next, as you can see, this value didn't update. The reason is because it sees that we already attempted to travel this path, but we didn't like this path. So it's going to ignore this path and only say that it has one neighbor, and it is immediately going to go up here and calculate all of its math. After that, it has 2 more neighbors. One of its neighbors is the winning square. So of course it goes to the winning square. However, due to the way it was programmed, because I didn't want to add in any extra code, it will also calculate stuff for this node. However, it will always go for the lowest f cost, which it will get when it gets to B. So that's a very simple demonstration of how this will work. And now let me just go through this a little bit faster. So as you can see, this will start off by calculating the values for each neighbor it has, and it will choose the one with the smallest f value, or if it's to the right. Next, it'll again calculate each value for its neighbors and choose the one either to the right. It'll either choose the direction that it wants, or it'll choose the costs that it wants. In this case, it chooses the direction because there is no cost value. Again, it'll do the same thing. However, this time there's still no cost comparison. It's just a direction comparison that's going on. Now, it can only go one way, so it's going to go that way. However, it will still calculate the values for that node. It can still only go one way, but it will still calculate the values for that node. Then it has two neighbors. One is the winning square, one is the longer square to get there. So of course, it chooses the winning square. So that was a quick rundown of how this works. And now we will be going to the Mac part. Sorry, I can't pronounce today. Anyway. So now we will be going to the Mac part, in which I will explain all my code, give you a link to the source code in the description, and all that good stuff. So let's get to the Mac part. So welcome back to the Mac part. Now I'm going to be giving you a quick demo, then going over the code. So let's get started. So as you can see, this is the simulator, and now I'm going to be testing the app in front of you. As you can see, the red point is point A, and the green point is point B. Now it shows you the the H and F values on the node itself. So when I click on the Pathfind button, guess what? Yep, it will find the path from red to green, and this is the shortest path it could possibly take. In this case, I'm not exactly sure for other cases if it would, but it probably would. And for example, I can place obstacles here and here, and it would find that I should go through here, around here, over the obstacle, and back on the course. That's really interesting. Let's just try obstacles maybe over here, over here, over here, over here, over here. This will force it to go around and in. So let's Pathfind, and as you can see, it actually just went this path. It did explore these, it tried to, but it didn't. And so that's what these sort of lighter colors mean here. The cyan here means that it explored this, it tried its best to go here, but it wasn't successful. And this dark blue path is where it actually went and where it was successful in going. Then there's this white where it didn't even bother, and then the green and the red, which I've already explained, and black are just the obstacles. So that's really it for that, and there's also, of course, a clear button. And now, let's get into the code. Now, we have a few classes here, such as block type, node, node view, and array extension. Let's start with block type. This block type enum, or enumeration, will allow us to see what types of blocks we can have. We can have air, obstacle, point A, point B, path, or explore path. So air is just white, obstacle is black, point A is red, point B is green. The path is the actual dark blue path. The explored path, where it actually tried to go, is the cyan. And you must be thinking, I'm not declaring cyan, etc., over here. How are you getting the value? Well, that's simple. In my node class, I have a color variable, which will allow me to get whatever color of myself which I am. So if self.type is not equal to one of these, it'll just return orange as a random color, because it has to return something. Okay, getting back to the main stuff. Then we have an array extension. This array extension has a few functions by some people. So this function, a mutating function, was created by Drawag. Sorry if I'm not pronouncing your name right, but this is a link to the Stack Overflow thread where he actually explained how to create a remove object from array function, and I just modified this function a bit, so if you want to download this source code, it will be in the description. Apart from that, we have a get function by Alex Wayne on Stack Overflow. Again, sorry if I'm not pronouncing your name right, but this is a link to where he answered this get function. And then this is the check index function that I've created, which if an index exists, it will return true, or else it will return false. Okay, so these are all being extended to the array class, and now we can get into our main parts, such as the node and node view class. For the first time, I haven't really used viewcontroller.swift. I'm mainly only using these four files. Anyway, let's get into node first, because that's smaller, simpler, there's no really much algorithms involved. This could be more of a struct if you think about it, but I just wanted to create this as a class. Okay. So now, this is one node on the screen. Not every single node, just one node, which extends NS object. It has a private variable called real type, which is by default equal to .air. This is the real type that the node carries, and this is always going to stay private. Then this is the x value that this node holds. Now you must be thinking that this is on the screen because that's obviously what it is. But no, this is in the array of the nodes themselves. So for example, if we had an array of nodes, a two-dimensional array of nodes, we could store that, okay, this node is at this x, this y, in this array, so that we could use it later. Then there's also the y value for it. Then we have the g, h, and f values. The g value is by default equal to -100, and so is the h value, as to be the lowest scores possible. And then for the f value, I think these are called properties maybe, I don't know exactly, but basically whenever you call this, whenever you get the f variable, it will always return g plus h. Because then we don't need to keep setting f, then retrieving f, then setting f, then retrieving f, then setting f, then retrieving f. We just retrieve f, and it'll always give us the latest updated output, depending on what g and h are. Next we have from. This is basically the node's parent. So for example, if we had from point A to the one to its right, its from would be point A. Then so on, so forth, until we had an array or lots of nodes from this node, that came from this node, that came from this node, that came from this node, etc., etc. Then we have the color, which is a UI color, and this is the color of the current node, which I've already explained to you. So this will return the color of the node that it should be. So if it's air, it'll be white. If it's obstacle, it'll be black. If it's point A, then it's red color. If it's point B, then it's green color. If it's path, then it's blue color. If it's explored path, then it's cyan. And if it's none of those, then it's orange. Yeah, because there was no other color I could think of. Anyway. Then we have the type. This is the actual type that we can access publicly, not globally, publicly, because we have to have some sort of a type variable in order to access it. The reason I didn't just create one proper real type variable here as public is because this will be private here. However, when we are setting our type, we might want to do something. So we create this public variable that when get, it will just return the real type. However, when you set, it'll actually set the real type to the new value that you're trying to give it. So it won't actually set itself. This means that basically, if we want to do something once we've set a new color or a new type, then we can actually put that code here. We have the freedom to do so. We don't need to add this much code just to do that. Anyway, now into the juiciest part you could possibly think of, the node view class. This is the actual UI view that we will have on our main.storyboard. And this is where all the magic happens. As you can see, this is very detailed commented code that you can just download, and you will be able to understand almost all of this. So basically we're creating a global variable called infinite, just because you know, I had to have something for the dummy g and h values that I create later. Not the -100 and -100 that you just saw, but you will see when I actually start comparing f values, I have to have a dummy g and dummy h value. Okay, next. This is our actual class for the node view. Then we have a size, which is a CG float for 4. I'm not exactly sure why I created CG float. Oh yeah, so I could actually multiply and divide nicely. That's why I created a CG float. Anyway, next we have the nodes, which is an array, a two-dimensional array of nodes. And this is just a blank array right now because we will eventually be filling it up with lots and lots of nodes. So then in our awake from nib function, we have a for loop. First of all, this one goes from this. Actually, if you didn't know already, just a swift quick tip. Just 1 second, sorry. Okay, coming back to this. Swift quick tip: if you put an underscore in a for loop or in an if statement or an if let statement, sorry, or in a while loop or in a do while loop or something, this will substitute for nothing, meaning it will not count this in any variable. That was pretty interesting. So for blank in 0 dot dot less than int size. This means that it will basically go 0 to 1 less than the size. So this will insert so basically this for loop will insert error into all the dummy nodes. So we'll create a final node, which is an array of nodes, and it will loop through 0 to 1 less than the size again, and it will create a new node. It'll set the node.type to error, and it will append that node into the final array. Then it'll append that final array to our node's two-dimensional array, so that we eventually get a two-dimensional array full of just blank nodes, a 4x4. Or if I were to change this, we could actually make this a 10x10 grid, if you really want to see what that looks like, in case you're one of those curious people that really wants to see a 10x10 grid. As you can see, the labels are almost unreadable, so just don't try to read those if you want the bigger screen. Anyway, as you can see, I can just make a few obstacles, and they should be able to traverse to it. As you can see, it has found the shortest path from point A to point B. That was amazing. So then it also explores these nodes, and this is very different than the Dijkstra algorithm, which would have explored a few more layers deep in, or the best first search, which would have literally just taken a much different path than this one. Okay, anyway, getting back to the point, which is our real code here. Okay, so now we have, after our wait from nib for loop, we have this little line of code. So this will create point A and point B on the map. So they will always be in the corners, if you just realized. Sorry. If you just realized, these will always be in the corner, no matter what size I give it, because it automatically adjusts. So for example, it'll do nodes int size -1, 0, meaning the x value of the last size, meaning this one, is equal to point A, or actually, yeah, so this is taking the y value first. So apparently this Swift thing will take the y value first, then the x value. So it's taking the y value, which is our size -1, which is over here, and the x value for 0, which is over here, and we're setting that to point A. And then we're taking nodes 0, y, but maximum x over here, and setting it to point B, as you can see. Then we are refreshing the screen with self.setNeedsDisplay. And then we are looping through 0 to 1 less in nodes.count. Then we are doing for j in 0 to 1 less than i.count, basically. So imagine this, a two-dimensional array. We're taking out a little array at a time, and then we're looping through that array one node at a time. So we're basically looping through all the nodes. And then we're setting the x and y value for each so that we can use them for reference later. Okay, next. This is just a simple function that will create a label wherever you tell it to, and with whatever text you give it. So then this function over here will be able to. Sorry, I'm not explaining the create label and touches began and touches moved functions right now in much depth. However, this is way too complicated to actually go through right now. But if you really want a more detailed explanation of this, you can just tell it to me in the comments or even mail me, and I will do something for you about that. But you can always download the source code in the description, and I will be giving you a brief summary of these functions one by one. Okay. So getting back to the point, we have the touches began function, which is overridden from UI view, and so this will get the location of your touch, calculate which node you must have touched on, because we aren't really doing basically it's very abstract how to find out which node you clicked on, because we always have to take our x value, divide it by the size, and so it becomes really complicated in that sense with lots of math and stuff. So you can just download it, check it out. But if you really want a more detailed explanation, again, mail me or leave it in the comments. So then, same thing for touches moved. However, this will be whenever they move, it'll keep on placing another block. When you touch move, I won't let you remove blocks, however, like I can for touches began, due to the simple fact that when its touch is moved, and if you were to keep it here and just move around a little bit, it would just keep going on and off. So it will get like, okay, on, off, on, off, on, off, really fast, and that would be very annoying sometimes, so I just turned that ability off. Then this function here will create a rectangle on screen wherever I tell it to with an orange border. So it's all of these are just CG rects put on with CG context. So that's why our touches began is so abstract. We can't just click and have it, okay, this node was clicked at this place. Because, of course, I mean, it doesn't keep track of wherever every single node is, and so that really interferes with how we calculate the location of your touch. Yeah, so this will just create the rectangle, as I said, and next. So then this function will return an array of nodes, and these are all the nodes which are neighbors for a specific node that you give it. So it will get the node X and the node Y, and it'll check above it, it will check below it, it will check to its right, it will check to its left, it will create a final array, it will make sure that all the neighbors match the criteria, and then it will return this final array that it creates. Okay, next. This is the function that we use to get the heuristic cost for from node to node. And this will return an integer always, and so it will return the absolute value of from.x minus 2.x plus absolute value of from.y minus 2.y, and then times this by 40. So that's a pretty complicated expression, but again, you can always download this, do this step by step, create the expression tree like we just did, etc., etc. Okay, next we have our real A* function, and you would think that this would be a gigantic function full with code that's really complex and not easy to understand, but if you think that, you're wrong, because this is actually quite simple, and so this is basically where all the dirty work happens, and so there will be a link to the pseudocode that I got from Wikipedia for this, which I had to it took me like an entire day, maybe 2 days, just to translate that pseudocode into Swift, since Swift is so much more different than some other languages. But anyway, I managed to get it done and ready for you to download. So this will basically create tentative G-scores, get the neighbors, reload our basically, what do I call it? It will reload our view over and over again, and etc., etc. Anyway, next what it's going to do, and by the way, it will actually return nothing, no nodes for the path. And this is due to the fact that if in our while loop, when we're doing the dirty work, we're checking if we have already reached our goal. If we have, then we return reconstruct path for the current path that we are on. What this will do is it will reconstruct our path from the ending node back all the way down. So what it'll do is, let's just say we've created a path from A to B. We will give it where we ended off from B, and it will backtrace to the beginning and return that array of nodes. So over here, as you can see, this is how we reconstruct, and yeah, that's a very simple function to understand as long as you know a little bit Swift. So it will create a total path nodes array, which is only equal to the current, and then while let par is equal to total path dot first dot from, meaning we take the first thing in the total path and we check if it's from. If there's nothing there, then we stop and we just return. Well, actually, we don't stop, we just skip this specific node, but then eventually we would have to stop because of it. But anyway, then we actually insert that from value to the total path, which is quite complicated if you think about it. So basically, we have the ending node, we take its parent, and then we take its parent, and then we take its parent until we reach the end of the line, and then we return all of those nodes that we found the parents and children for. That's how that works. And this is the lowest f-score function that I created. This will find the lowest f-score in the entire array of nodes, and it will return one node with the lowest f-score. So we'll create a final node, which is equal to a new blank node. It'll set its g value to infinite, it'll set its h value to infinite, and that's why we're using that infinite constant that I created before, and then we are just searching for the lowest f value and just making sure that it's not minus 100, and then we're just returning that final node. It's that simple. And anyway, when we draw rect, however, this is way too complicated to explain right now, but what's basically happening is it will remove all squares that it currently has, and then it'll detect the width for each little rectangle, the height for each rectangle, the x and the y for each rectangle, and then it'll just loop through all the nodes, create the actual rectangle for each one of them, set the x and y values accordingly, create a label under them that can easily, also by the way, the labels fonts will automatically adjust depending on what size they are, or the text and the actual rectangle. So that's interesting. And it will also reset the x and y values accordingly. Okay, so that was the draw rect function, but I had also skipped a few functions before because I didn't want to focus on those yet. But anyway, now let's get back to them. In our clear function, we're just resetting all nodes, and when we reset all nodes, you know that we are basically clearing every node and doing whatever we did up in the viewDidLoad function over here. Awake from nib. Whenever we awake from nib, that's what we want to do. We want to basically reset all nodes. And that's it. But when we reset nodes, all this means is that we are clearing only the blue nodes that are for the path, so that next time when you pathfind, those blue path nodes aren't still there bugging you, just like those are actually the current path. But no, it'll actually take away those blue paths before it continues with its pathfinding. So that's interesting. Apart from that, there's not much in this, really. And when it solves, all it does is it will reset the nodes, of course. It will create a path, which is equal to a new A star. So this is a new A star instance, and we're giving it from the nodes point A to the nodes point B as its goal. And then we are just looping through its path, which is the reconstruct path, that we just got from that function. And for every square that it actually gives us, we want to set it to path, and then make sure we just set the squares back to point B and point A, and then we just refresh our view so that we have the latest stuff. And now, just to prove it to you, let's just set this to 100. I'm not sure if this will crash. It might, because 10,000 grids. I don't think it can handle it. But why not try, right? Okay, so as you can see, this is way too many grids for it to handle. I can literally just draw on this and we wouldn't even see it. This is way too many, but if we were to pathfind, it would probably crash the iOS simulator. And as you can see over here, this is using up 99% of my CPU. It's using up around 300, maybe even getting up to 400 back it is 250 megabytes of my memory, and yeah, it's really just very complicated how this is working. Apparently it hasn't been able to find the path yet, or actually it may have, but whatever. That was it for this tutorial, and yeah, just one second though, I just remembered something. Yeah, so that was pretty much it for this tutorial, I guess. And yeah, so yeah, just give me 1 second though. Yeah, and just before I go, because this wasn't really practical, 100 by 100, why not try 20? So you can actually see it works on pretty huge grids. As you can see, this is still very huge. We can like draw something around it, and then we can also just create a simple little obstruction. Sorry, it's taking a little bit of time, but this will really prove to you that this can find its way through the most difficult of mazes. Well, actually, I didn't include a maze generation algorithm in this, but I will soon, and maybe just upload a part 2 to this. So now if we were to Pathfind, as you can see, it explores a lot of nodes because obviously this is a pretty open sort of ground for it to play on. But I mean, it works eventually. It actually works much better than some pathfinding things that I've seen. What I would like to include, though, is something called look ahead, meaning that it would actually look ahead from this node and say, okay, why go here when I can just go here? But that's for later, maybe part 3 after I include the maze generation. And yeah, that was it for this video, and I'd like you to please subscribe to my channel if you like my content and you want to see more of it. Please like my video if you liked it, comment if you have any suggestions or questions. You can even email me for those. My email will be down in the description, but just in case you want it right now, it's tadgymani@gmail.com. Again, all Wikipedia pages will be down in the description, such as their Wikipedia page on A-Star, Dijkstra, and Best First Search, since they're all related to this app. We will also have the Stack Overflow questions related to the array extensions that I use, and that's gonna be it. Goodbye.